In this video SOP, we'll take a look at the Alpha Laval Disc Stack Centrifuge system and learn how to set up and operate the equipment for use in processing material generated from microbial fermentations. Here, we see the researcher carefully moving the equipment from the storage rack to the main process floor. The unit is quite heavy, so it is important to handle using the metal frame while moving slowly to avoid losing control. Once the equipment is in place, lock both casters on the front side of the equipment to ensure the unit will not move during operation. From the back of the equipment, we see the motor and transmission unit as well as the bowl of the centrifuge where the separation process occurs. We will now review all the steps to set up the centrifuge as seen in order to process material. Safety. There are a number of important hazards to be aware of while operating the Disc Stack Centrifuge. First, the equipment requires a high voltage electrical power source in order to drive the motor at high speeds. In the unlikely event of a malfunction, shock or arc flash from a 480 volt source can cause serious injury or death. Therefore, it is critical that researchers have completed the requisite electrical switching training and wear appropriate PPE while powering the equipment. Second, the process floor may be crowded with various containers and hoses, and the floor may be wet at certain times. Therefore, it is advisable to wear slip-resistant safety shoes and to be mindful of the appropriate paths around the equipment to avoid tripping hazards. Third, during operation, there are large amounts of kinetic energy in the rotating unit, which may spin up to 10,000 RPM. It is critical that the rotating unit is slowed to a complete stop and the equipment is fully powered down before any disassembly is attempted. In addition, be mindful of any excessive vibration or noise from the equipment during operation. In case of a malfunction, push the red emergency stop button on the front panel and leave the room immediately. Additional hazards that are not covered in further detail include hazardous material handling, including biological material and caustic cleaning solutions, high pressure utilities, including road water, house air, and chilled water, heavy equipment, including the centrifuge skid, holding tanks, drums, buckets, and scales. Equipment preparation. A variety of sanitary hose connections are required for the centrifuge to operate. First, a road water source is connected to the operating water inlet port. A gasket is placed between the sanitary fittings, then a tri-clamp is placed around the fittings and tightened by hand to ensure a secure connection. A second road water source is then connected to the flushing water inlet in a similar fashion. Third, a hose is connected to the drain outlet port, then routed to the nearest floor drain, allowing the centrifuge to discharge effluent water directly to the drain during operation. Fourth, house chilled water is connected to the cooling water inlet port. The yellow tape on the chilled water hose denotes this is the supply line. The outlet port for the cooling water is then connected to the return hose of the house chilled water, which is unmarked. Next, a hose is connected from the process material source to the feed pump inlet. In this case, the source will be the harvest port of the fermenter, not shown. Then, a hose is connected from the feed pump outlet to the process liquid inlet on the centrifuge. The next connection is made to the clarified liquid outlet port. This hose is routed to a collection vessel such as a drum or holding tank for the clarified material. Finally, a hose is connected to the sludge outlet port and routed to a collection vessel. This allows the concentrated sludge to leave the centrifuge during discharge cycles. This overhead diagram summarizes all the sanitary connections required to run the Disc Stack Centrifuge. Utilities. Process air is required to operate pneumatic valves and the discharge pump on the centrifuge. The long, flexible air supply hose is connected to a house air source and the hand valve is opened. Next, the supply valve for the Roadie water is opened. The hand valve on the Roadie supply hose for the operating water is opened along with the secondary valve on the centrifuge, located after the pressure regulator and gauge. Similarly, the hand valve is opened on the Roadie supply hose for the flushing water port, though there is no secondary valve in this case. Both valves for the chilled water supply and return are open to allow recirculation to the house system. After donning leather gloves, the electrical cord may be connected to a 480 volt power source. The technician then steps to the side of the breaker box, looks away, and switches the breaker to the on position. Do not perform this step unless you have completed the requisite electrical switching training course. Next, turn on the main power switch located on the side of the centrifuge. The unit is now fully powered on and will begin the boot up sequence. Finally, connect the feed pump to a standard 110 volt power source and ensure the switch on the back of the pump is in the on position. This overhead diagram shows all the utilities along with the sanitary hose connections made previously. The equipment setup has now concluded. Flow paths. Processed liquid is pulled from the harvest port of the fermenter into the feed pump and then into the inlet port of the Disc Stack Centrifuge. The feed material then passes through a flow meter and enters the clarifier through the central port at the top of the bowl. The feed material moves down the feed pipe and enters the separator bowl at the bottom, where it is exposed to centrifugal forces that move the denser sediment to the outside edges of the bowl. The lighter clarified liquid flows through the disc stack back towards the center of the clarifier and is pulled out of the chamber by the pairing disc, continuing to flow out of the equipment to an external collection vessel. Sediment will continue to collect at the sides of the bowl and form a sludge throughout the cycle, thereby reducing the effective bowl volume and separation efficiency. The sludge is discharged at high velocity at the end of each cycle, where it first decelerates in the cyclone, then is pumped out of the equipment to an external collection vessel. Startup. After powering on the equipment, the centrifuge will default to the standstill mode, as seen on the control panel. The operator can push the corresponding button to start the centrifuge. While in the starting mode, the centrifuge will begin to spin and steadily increase the speed until the target RPM is reached. At this point, the mode will automatically change to standby until further action is taken by the operator. Routine checks. A few routine checks are conducted with water to make sure the equipment is functioning properly before introducing any processed material. A water source is routed to the feed pump, which is set to a flow rate of 2 liters per minute. Then the operator will move into the production mode, which will allow the feed water to flow to the clarifier. While no actual separation is occurring in this test, this is a good opportunity to inspect the equipment for any excessive noise, vibrations, or leaks. The clarified liquid and concentrated sludge outlets are monitored closely to ensure correct operation. Specifically, at each discharge point, the volume of sludge discharged is measured to ensure there are no internal leaks or blockages in the clarifier assembly. The expected discharge volume is 1.1 liters. It is recommended to run through the test sequence for 3 to 4 discharge cycles to ensure the centrifuge is operating at steady state. In the case of insufficient or excessive discharge volume, the centrifuge will need to be shut down, disassembled, thoroughly inspected, then reassembled in the correct manner. Before doing so, it is important to verify that the operating water pressure is within the appropriate range, as this parameter has a large impact on the discharge performance. Operating parameters. There are 2 main control parameters that dictate the performance of the centrifuge: the flow rate of the feed material and the discharge interval time. To approximate the optimal parameters, the feed material is characterized by determining the relative amount of solids in suspension. This can be accomplished by a simple spin-down test in a graduated tube. The total broth volume and resulting solid pellet volume is used to calculate a packed cell volume, expressed as a percentage of the total broth volume. This value, along with the target flow rate and target solids percentage in the sludge, is input into a simple mass balance, which takes into account the maximum volume of sludge that can accumulate in the bowl before a discharge is necessary, and calculates the corresponding discharge interval, in this case 4 minutes. Note that the discharge interval is inversely proportional to the feed flow rate. As the throughput is increased, sludge will accumulate faster and require shorter discharge intervals to clear the material from the bowl. Maximizing the throughput is desirable and will result in shorter processing times. However, there is a trade-off, as increasing the feed flow rate will reduce the nominal residence time and separation efficiency. It is important to consider this trade-off when selecting processing targets. The operator adjusts the flow rate of the feed pump to the correct value, followed by specifying the discharge interval on the centrifuge control panel. This equation is a good starting point and tends to yield conservative results. The next section will discuss how the live process is further optimized by monitoring and adjusting these parameters. Material processing. Now that the centrifuge has been thoroughly tested and the process material is characterized, the separation process is initiated by connecting the bioreactor harvest port to the feed pump, then selecting the production mode on the centrifuge control panel. To the left of the control panel is a display for the turbidity sensor that monitors the clarified liquid line. The measured turbidity value may gradually increase between discharge cycles, indicating an increase in cell carryover as the bowl volume decreases due to sludge accumulation. A rapid spike in the turbidity value indicates the bowl is saturated with sludge and that an immediate discharge is required to reset the separation. On the control panel, the operator can monitor the feed flow as measured with the flow sensor and adjust the external feed pump if necessary. Shown here is the control panel screen as a discharge occurs. As the counter reaches 0, the discharge message begins to flash and the counter resets to the interval. The feed valve is temporarily closed to allow the bowl to evacuate completely, then is reopened. The discharge is typically configured to run for 60 seconds. A sample of the clarified liquid is taken near the start of the discharge cycle, as this point should represent the minimum separation efficiency due to the sludge accumulation in the bowl. A sample of the concentrated sludge is taken during the discharge period. It is also advisable to regularly measure the sludge discharge volume to confirm that sludge is completely ejected from the bowl. Both samples undergo a spin-down test and are inspected to ensure the separation is effective. In this case, since there are no visible particulates in the clarified liquid and the sludge is only at 50% solids, the feed flow rate can be incrementally increased. Sampling is conducted at the next discharge period to evaluate the effect of the parameter changes. No particulates are present in the clarified stream, and the solids fraction in the sludge has increased to 60%. Thus, the feed flow rate is again increased up to 88 liters per hour. Again, the process is sampled to monitor the effects of the change. Here, there is a visible pellet of particulates present in the clarified stream. The sludge stream is around 75% solids, which is about the maximum viscosity that can be handled by the discharge pump. Thus, the feed flow rate is slightly decreased to 83 liters per hour to boost separation efficiency, and the discharge interval is increased to 4 minutes and 15 seconds to maintain the solids fraction in the sludge. These parameters result in a pellet-free clarified stream and a sludge stream with the maximum allowable fraction of solids. Thus, the process has been optimized and will continue to run with these final conditions for the duration of the processing. Once all the material has been processed, the operator can shut off the feed pump and change the centrifuge into standby mode. Cleaning in place. After processing all the material, the centrifuge will need several stages of rigorous cleaning to remove deposits from all interior surfaces. In the first cycle, water is used to flush out the majority of residual material. A bucket of road water is connected via a hose to the feed pump. Then the valve is opened for the flushing water inlet hose, and the operator can start the feed pump at 2 liters per minute, or up to 7 to 9 liters per minute, and change the centrifuge into CIP mode. In this mode, flushing water supplies various spray nozzles that are activated to displace materials inside the clarifier assembly. Due to this extra water, the typical discharge volume will be around 4 liters. Both the clarified liquid and sludge discharge streams are collected in a drum or other collection vessel so that residual cells can be properly deactivated before disposing of this material to the waste treatment unit. This flushing will continue for 5 discharge cycles or until the effluent streams are relatively clear and free of particulates. Next, a 1 to 2% CIP 100 solution is made up to feed a caustic cleaning solution that will better dissolve protein deposits inside the centrifuge. The CIP cycle is continued as before. However, in this case, the clarified liquid and sludge discharge streams are placed back into the CIP 100 solution feed bucket so that the solution is recirculated during the 10 to 15 discharge cycles. Due to the caustic nature of this solution, it is critical to secure and monitor the hoses to avoid spilling or spraying this solution. A final flush using Rhody water is performed to clear out residual cleaning solutions where the effluent streams may be collected with the flushed material from the first stage or discharged directly to the drain. This stage will continue for 5 discharge cycles or until the effluent water stream is confirmed to have a neutral pH, as tested by a pH test strip. After confirming an appropriate pH, the operator will change the centrifuge into standby mode. Equipment shutdown. Now that the clean in place cycle is complete, the operator can change the centrifuge into the stop mode, which will gradually allow the bowl to decelerate to a stop. This may take upwards of 20 to 30 minutes. The speed can be monitored on the control panel, as shown here. After reaching a complete stop, the centrifuge will perform a final discharge of any liquid remaining in the clarifier bowl. At this point, the main power can be switched off on the centrifuge, followed by the 480 volt breaker on the wall. Then the power cord is removed from the outlet. The remaining utilities are also shut off, including the air supply, cooling water send and return, Rhody water supply valve, and the hose valves for the flushing and operating water. Now all the hoses can be removed from the centrifuge manifold. Note that some residual liquid may be present in the lines, so it is advisable to place a tray underneath to capture any discharge while removing the hoses. The cooling water loop has a dedicated drain valve that can be opened to depressurize the loop and direct the residual water into the tray. Finally, ensure that all hoses, gaskets, and clamps are removed from the centrifuge and placed in appropriate locations. Then, unlock the front wheels and carefully move the centrifuge back to the storage rack until further use. Once the wheels are locked and the safety cables are secured, the operation has concluded.